Welcome everybody for our QuMat seminar. The guest this time is Pantelis Bampoulis. It's a very beautiful, different because he comes from Greece, where he also did his studies, his bachelor studies. And then he came to the Netherlands, to Twente, to do his Twente University in to do his master and PhD. After that, he got a Humboldt fellowship and he went to Cologne, where he did his postdoc. And from 2018 to 21, and then in 21, he got a penny and came back to Twente. And last year, he got very rich because he got a starting grant from ERC and Avidi, so he has a huge group right now. He works on low-dimensional systems, transition metal dipolymerides, germanene, and the technique is scanning tunneling microscopy and spectroscopy. So we are very glad to have you here today. Pantelis, please go ahead.
Thank you very much, Cristiane. I'm also very happy to be here today and I'll discuss beforehand with you and also give a colloquium for the QuMat. And of course, thank you for the invitation to be here. So I will talk about germanene and the work that we do in Twente on germanene, in particular germanene nanoribbons. But before I do that, let me start with acknowledging the people that are involved in this work. And I would like to start with saying that this is, in essence, a QuMat collaboration, so that is, I think, quite nice. And theory, we have the side of Utrecht, so Cristiane and Lumen. And then in Twente, well, you can see you're probably familiar with some of the names here. So I would like to mention Dennis and Esther, the PhD students that did most of the work. Of course, Harold, and there is a bit longer list there. There is quite some contributions from the group of Mikael Katznelson and also Morais as well, what I'm going to show you today. So let me start by briefly introducing two-dimensional topological insulators. I think there is no need for a long introduction here, as most of you are probably very familiar with these topics. Essentially, since it's I think a big pillar in the QuMat consortium. So, but what is a two-dimensional topological insulator, and why we care so much about these materials? So these are materials that have some unique properties. So when you talk about this two-dimensional systems, then you have something that is insulating in the middle or in the bulk of the material, and it's metallic or conductive at the edges. Now these edges are more special than this higher conductivity. They are spin polarized, which means that spin momentum locked, which means that spin up electrons move in one direction, while spin down electrons move in the opposite direction. So this spin momentum locking, together with the time reversal symmetry, they are time reversal symmetric, these two copies, they prohibit backscattering from non-magnetic impurities. So if you have a normal sample and you haven't introduced any magnetic impurities, the current that is moving, or the electrons that are moving along these edges, should happen in a dissipationless way. So therefore, you can think, if you can implement these materials in a device application of some sort, you could achieve some low dissipation or almost no dissipation. But it's quite interesting from a perspective of low energy electronics. On top of that, you can induce topological phase transitions, and I will show you a few of them today, which allows you to have this fast switching mechanism. It's different than conventional transistors or field effect transitions, where you have to deplete or you have to accumulate charge carriers. So it gives you more flexibility, new mechanisms to play. Well, they are quite interesting materials. Just to recap a bit, in principle, they promise charge transfer without dissipation, right? Because this backscattering is forbidden. Fast switching mechanism, through these topological phase transitions. And last but not least, if you engineer them, you could also achieve new states of matter. And for example, zero energy modes. Because of that, there is quite a lot of work in trying to make 2D topological insulators, and there are quite a number of examples. So in my presentation, I'm always quite biased towards STM. I like STM, so I always choose papers that are have a beautiful STM images to show. So, but you are, I think, quite some of you quite familiar with BIS-within. So it's a large bandgap punishment hole or 2D topological insulator. But there are also other systems, 1T prime, tungsten selenide or tungsten telluride. And the system that I will be discussing today is germanene, which we also very recently saw that it is also a 2D topological insulator. Just to briefly introduce you, what is germanene? So germanene is a material just similar to graphene. So it has this honeycomb lattice, but instead of having carbon atoms there, you have germanium atoms. Now, this has an implication because, well, germanium is quite heavier, quite bigger compared to carbon. So the germanium honeycomb lattice acquires a buckled configuration. That means that half of the atoms are slightly displaced, vertically displaced from the other half. So typically for a freestanding germanene layer, this buckling is in the range of 0.6 to 0.7 angstrom. Now, if you look at the band structure of germanene, forget about spin-orbit coupling. You take the tight binding model, you get just like in graphene, you get these Dirac tones that cross the Fermi level at the K prime points of the Brillouin zone. But because germanium is heavier, spin-orbit coupling is quite significant compared to the case of graphene. So you get a gap between the spin-orbit coupling. Now, the spin-orbit coupling in the system will open a band gap at the Dirac points, and it will act effectively like a magnetic field in the 2D germanene layer. So it will push spin-up electrons to move in one direction and spin-down electrons to move in the opposite direction. So in principle, you should get the quantum spin Hall effect there, and you are dealing then with a 2D topological insulator where you have this spin polarized states, a spin up state and a spin down state, crossing the Fermi level and connecting the conduction particles from the K to the K prime point and vice versa. And here are depicted in this cartoon. Okay, so this is the theory. We were able to make germanene a long time ago. And just a moment ago, Cristiane gave an introduction about my career so far. I did my master in Twente, and actually the germanene layer was grown during my master project. So it was serendipity. So I was trying to make nanowires on a vicinal germanium 110 surface, and by accident, we found this buckled honeycomb lattices. So I had in my in the logbook at that time I had a big question mark, and then it just stayed there for a couple of months until we went through the data and so on. Then okay, so this is, you can see the scanning tunnel microscope image over here. So you can resolve the honeycomb lattice, and you can see that it's actually buckled. So you see that half of these atoms are brighter than the other half. Of course, you're talking about STM here, so characterizing this buckling is a little bit difficult because you also deal with all of the density of states together with your it's always a super it's always in a signal. So, but you still can make out the lattice concept, which is about 0.42 nanometers. That's what you would expect for a low buckled germanene lattice. You can measure step heights because this grows in layers and with different thicknesses. And we also could extract a buckling, which changes a bit with the bias set point, but it is in the order of 0.03 to 0.04 nanometers. So it's about half of what you would expect for suspended or freestanding germanene. That can be explained because you have these interactions from the substrate. Now we look at whether it has the properties you would expect in such a system. And this is an example of scanning tunnel spectroscopy. This is DIDD as a function of sample bias, and this is a signal that is proportional to the local density of states. So if we do measurements on a germanene flake, at the middle of the germanene flake, this is the wide spectrum over here, you see that it has a gap-like feature around 0, whereas the edge itself lights up also in these DAV bumps, and it has quite pronounced metallic states. So we can we see that it did this prediction of this edge bar correspondence. It is also experimentally there. Now, if the system is truly topological, you would expect, because you have this buckling, to be able to change between the topological states. So theoretically, you would expect that you have this band structure over here. By applying an electric field in the system to break the band inversion symmetry, that will lead to spin splitting of your bands. And for example, over here, the spin, let's say blue are the spin out bands, or and red are the spin down bands. The spin out bands and the K point move close together. Whereas that happens for the spin down bands in the K prime point, and vice versa for the other bands. Now this will lead to a closure of the gap, so the system essentially should become semi-metal. And then if you keep increasing the electric field, then you will be open a band gap. And we can apply experimentally such an electric field because we have an SDN tip. So you get that, in a way, you get that for free, because as you bring a tip of a certain material which has a certain work function enclosed to a substrate with a different work function, so you get what's called a built-in electric field. And that built-in electric field will depend on the distance, on the work functions, of course, but also the distance between the tip and the sample. So by changing that distance, then we have a good control, quite accurate control of changing the strength of that electric field. On top of that, you also have sample bias contributions, but because we are dealing around 0, these are weaker compared to that built-in electric field. So typically we have electric fields, or we have work functions for the tip in around 5.5 eV, and the work function of germanene is in the range of 4 eV. So we're dealing with quite strong built-in electric fields, which we can then tune with this distance that is over here. So we did this. We tried then to repeat this the expectations here from the theory. We tried to do it experimentally, and we saw that indeed, if you measure the band gap and you simply bring the tip closer and closer to the surface, the strength of the electric field builds up, it gets stronger, and you see that the band gap slowly closes. You get this like V-shaped character against the DIDB, which is reminiscent of a Dirac bone or a semi-metal. And then after that point, you keep increasing your electric field, and then you'll be opening band gap. So we could do that, and with we can do that reproducibly, also between different layers. So there's different samples and so on. So we can go, as you can see here, from a phase diagram. We can go from a topological insulator with the edge states to a trivial insulator with where these edge states are also gapped. And very recently, we also that this effect, this switching mechanism, it's also strong up to room temperature. So we can see, even though thermal convolution does not allow you to really resolve your gaps, you can still see the switching of the state on and off up to room temperature. So we have I would say, a very nice system to study. Also, new physics here with large enough band gap. You can see from this DIDV curve over here that our band gap is in the range of 50 to 100 millieV. We also have control, so we can switch it between a topological and trivial state. And as I will show you in the rest of my talk today, it's a system that allows you to further engineer it and access new states of matter. Okay, we did this with a 2D germanene. It's quite old news, but what are there any other challenges we can tackle, or any other new things we can do and we can explore with such a system? What comes immediately in my mind when I think of topological states is, well, I have a 2D material, I have one edge going all around that material. So I have very limited number of edges essentially. So if I take that 2D flake and I put contacts, I only have one edge going around. So if I think of very conventional types of applications, and I think of a ballistic conductor theory, then I know that my contact resistance will be very, very large. So the contact resistance scales with the number of modes. So if you have 2 modes, then you have a contact resistance in the order of 12.9 kiloohms, which is huge. So practically, even if you have dissipation as transferred in the channel itself, you still have a very large contact resistance. So it's a bit, yeah, is it practical? I don't know. What you would like to do, therefore, is to increase this number of channels. So to find a way to pack many topological states next to each other. So to maximize this density of topological states, I think that from a practical point of view, that would be very interesting. That will require to engineer things there and understand the interaction, engineer the interactions. Maybe that will also lead to new states of matter, and to keep having, or you still want to have this control, because you still want to control the system from on to off, for example, from having the states to not having the state, especially if you want to think of a transistor type of application. So I will talk about this stuff and what is the progress that we have had the past 2 years with this kind of work. So you can think of 2 ways of stacking topological states. Either you take 2D flakes and stack them on top of each other, and you hope that the interaction between these layers is weak and they keep their character, the topological character. Typically, you get quite strong interactions, but then at some point the system transitions to something else. The other way is to take that flakes, to take this 2D system, make it very narrow, essentially make something like a nanoribbon, and then stack it in a parallel way, next to each other. This is the way that I'm going to show you today. So you have then topological states that are next to each other in a very parallel way. So if you take a very wide flake, the end states over here, they're far away from each other, so there's not a big, they don't feel each other, there is no interaction. But the moment you go thinner and thinner, or narrower and narrower, and you also stack them very close together, the first thing you might have is that the electronic properties of the system might depend on their width. The second thing is you can have interactions. So you can, even within the same ribbon, you might have interactions from one edge with respect to the other. But if you also pack them very close together, there might be interactions between opposing ribbons. So if you want to do something like this, you have to first make the material, but also understand all these interactions.
Do you mean, let's say, Coulomb interaction or hybridization?
Hybridization, essentially. Yeah. But you could also think of, if you think of parallel linear liquids, you could have Coulomb drag or things like that, right? So that could also be there. So the question that we asked there is, how interactions also affect the system, but how small we can also make such a ribbon that it still keeps its properties, and what happens beyond that limit. So, okay, so we took our 2D flakes again. We have a growth method that is quite controlled, and we can make them. And that involves, it's a little bit of a complex process, but it involves eutectic liquids. So essentially, we deposit a lot of platinum on top of germanium. We talk about a few monolayers. We heat up to a eutectic, to a temperature where you have a eutectic composition that melts, so that you form this is low energy electron microscopy images, and you form these droplets. So now this droplets are injected liquid, they're really liquid, they move around, they coalesce, they do all kinds of weird stuff, and they have a composition of germanium 78% and platinum 22%. Now, if you cool down, they will decompose because the amount of germanium that can exist in the frozen phase within such a phase here is lower compared to the high temperature phase. So this decomposition is called spinola decomposition. So you end up with small clusters where they have a composition of germanium to platinum. We know this from Kikuchi scattering experiments. And on top of that, you see that the composition is different. You have extra germanium in the droplet. This extra germanium then will escape and some of it, or most of it, traps on top of this crystallize. Here you see a few of them. This is a scale of 20 microns, so we talk about a range of half 1 micron. These are the 2D flakes. And we can make them very big right now because the trick is to make these droplets as big as you can. And you can do that by staying at this high temperature for very, very long times. About a few hours, for example. Then the droplets coalesce, they get bigger, and then when you do the decomposition, also your 2D flake is very big. But if you look at such an image, you also see some elongated structures over here. So we understand these little dark spots, but we don't understand at the beginning they were coming. Sometimes they were in the experiment, other times they were not there. There was quite a bit of inconsistency between one experiment and the other. So the question that we have is what are these elongated structures? So if you look with STM, they look like this. So they're parallel arrays of something that's very elongated. And they can even run up to a micrometer distance. So they're quite long, they're very narrow, and they are parallel next to each other, especially in these high density areas. So recently we could optimize this process, and we realized that if we don't wait long enough at this high temperature here, and we simply flash anneal, the platinum does not really have the time, or the droplets do not have the time to accumulate a lot of platinum and to coalesce together. So you have a more spread out platinum on top of the surface. And we saw that if you do that and you cool down, then germanium likes to segregate on top of the surface. So what we have here is that result. So it's germanium from the bottom that segregates on top of the spread out platinum layer that remains on the surface. And these have these elongated structures because the crystal that we use is a 110 cat germanium. So, and that has an anisotropic large structure. So that follows the same crystal orientation as the substrate. We have looked at the structures. We can draw them with quite consistent way, and we can they look a bit like this. I don't know if it's so visible with the contrast, but I hope you can see it. And if you now zoom in on top, we also have seen that this phase is a germanium phase on top of platinum, and it's a growth that is also matching experiments that were done with silver. So it's a process that can be done not only with platinum but also with silver. And the reason is that germanium simply likes to go on top of the platinum. More of the platinum likes to be to travel between the germanium surface layers. So this is germanium. If we look closely with atomic resolution, we see that again it has a honeycomb lattice, similar to the 2D layer. So you have this honeycomb structure, lattice constants 0.4 about 0.42 nanometer, just like germanene, 2D germanene, and buckling a little bit smaller, at least what we can extract from the STM data. So we think that these are indeed germanene nanoribbons, and then you get these parallel arrays next to each other and so on. So to check that, we wanted to look at the electronic structure of this with scanning tunnel spectroscopy. So we took again a nanoribbon over here, and we looked at the edge and in the middle of the nanoribbon. And again, you see that the middle, it has this gap-like feature, while at the same energy range at the edge of the nanoribbon, you have this pronounced state. So again, we have this edge-bar correspondence, and you can even map it both sides, and you see that both sides are metallic with a pronounced state. You can even map the whole nanoribbon. So there's another example here where you have a nanoribbon that terminates, and you see that the end state is just running around the whole ribbon, just like in the case of the 2D flake. Now you can think of, okay, we have a lot of ribbons, arrays of ribbons that are parallel to each other. Are the states for every nanoribbon? They are there. The differences, of course, there's things that are still happening that we don't understand, but these are nanoribbons parallel to each other, and you see that you have more metallic edges compared to the rest of the surface. So you have, yeah.
What's causing the height difference between the difference?
Yeah. The height difference here, you mean?
Yeah.
Yeah, it grows into like a step like. So we think that it's coming from the substrate. So it's not that you have a bilayer germanene or multilayer germanene. It's a step height from the substrate. At least it's matching with the step height of the substrate and not with other germanene. So it's something that is probably coming from the substrate. So we have some. So we do have parallel edge states, and we have seen that you can even have a very high density of these parallel states, something like in the order of 60 to 70 states per 100 nanometers. So you might think, okay, what happens? Why we cannot stack even more? That is what I will show you in a moment. Is that you are limited to consider higher densities due to some quantum size effects that are happening. As you make the nanoribbon smaller and smaller, or as you perhaps also bring, if you bring two nanoribbons very close to each other, there might also happen things there. Okay, so the first thing that we want to look is what is happening then as we reduce the width of the nanoribbon. So we look at nanoribbons. You can see another example here of many nanoribbons, and you see that some of them are a little bit wider than the other ones. So we want to look at the width dependent electronic properties, and this is an example of that. It's a very wide nanoribbon here. You again have these metallic states at the edge. And as you make the ribbon narrow, smaller, or narrow and narrower, then you 3.6 nanometers, you still have an edge state. 2.4 nanometers, you still have an edge state. But at some point around just below 2 or 2.4 nanometers, both edge, this is the red curve, and bulk, this is the white curve, have now the same DIB, and both are devoid of any peak or any edge state. And it looks more like a gap-like feature, so something that is the DIB is decreasing at least around that energy range. So what is happening over here? So we see that the edge states are preserved all the way down to about 2.5 nanometers, and below that something is happening. That's where we contacted with Cristiane and Lumen to understand it a bit. So essentially, this is calculations for a wide nanoribbon, and this is calculations for a very narrow nanoribbon. You can compare this to a 1 nanometer, so two honeycombs next to each other, or 2 hexagon wide nanoribbon. And what you see is that for a wide nanoribbon, you have your edge states. But the moment you make it very narrow, over here is the edge state. You see that the edge state does not fully close the bulk gap, so it's gapped out. There is a gap or a mini gap that is forming at the edge state. And then from the calculations, it can be seen that within that gap, they reside, over here, they reside zero-dimensional states that are localized at the ends of the nanoribbon. And from the theory, you also expect that these zero-dimensional states are topologically protected by mirror and time reversal symmetries. And so you bit more, wider topological also, you see that the state is really localized at the end in the calculations. And if you calculate exact phase and then extract the topological invariant, you see that this phase diagram for the topological invariant over staggered mass staggered mass is this vacuum that we have in the system, is this staggered potential that we have in the system. You see that over a wide range of staggered masses for this 2 hexagon wide nanoribbon, you have a topological invariant of 1, which means that it's a topological system. And if you exceed that range, then you go to 0, which is then it means it's trivial. So the calculation for some, okay, that you lose your end states, but you should still have or gain your end states. So
still have spin properties. It's these end states.
and we had a bit of discussion about this before. We think that they should have fractionalized charges. So half of the, or part of the electron lives on one end and the other one on the other end. So the question was, from Newman and Cristiane, I said, okay, can you see that in the experiment? So let's look at, let's compare the theory with the experiment. And look at the edge, but also at the end of the nanoribbon at the same time. So on top here is the theory of the local density of states. At the bottom here is the DIV over the sample bias, so something that is proportional to the local density of states. And what you see with red over there is the top. This is the nanoribbon over there, the top and the bottom edge. White is the middle of the nanoribbon, and blue, light blue, is at the end of the nanoribbon. This is a very wide nanoribbon, about 5 nanometers, so you see essentially that the edge state runs around the nanoribbon, and there is not much difference between the two edges of the end. Same thing in the theory. You see that the ends, the end of the nanoribbon and the edge of the nanoribbon are about the same. There's a little bit of a difference between the actual shape of the what you would expect from a topological state is that it's a 1D state, so it should be constant, filling the gap, right? In the experiment, however, because you have something going from K to K prime point, it's a zigzag edge, you have, and tunneling in STM is predominantly happening from gamma point. You have this K parallel contribution, which leads to kind of like a Gaussian shape of your density state. So instead of having a constant shape, you have something that is decaying with voltage. That's why we have this discrepancy between the two. But we can understand this well, and we can also fit it, and it fits well. Okay, so if we go now to a narrower nanoribbon, so now we talk about a 6 hexagon wide nanoribbon, we see in the theory that the edge states, you can see that there is a little gap-like or deep that you have around 0, whereas that doesn't happen at the end. So the end still is very prominent. You also get a peak at this location, indicating a 0D state emerging there. If you do now the same with the experiment, you kind of see something similar. So you see that the end of the nanoribbon lights up, which has a stronger peak compared to the edges. And now we go to the case of a very narrow nanoribbon. This is 2 hexagon wide, and now you see that in both in the experiment and in the theory, the edge states are gapped. So edge and bar have approximately the same density of states, but at the end of the nanoribbon, you end up with a very sharp peak in the density of states, again reminiscent of this 0D modes that you have at the end of the nanoribbon. So we have a very good agreement between theory and experiment that this phase transition leads to the emergence of 0D states that are localized at the end of the nanoribbon. Now you might ask what's happening in between these two ribbons, between 6 and 2 hexagons. A lot of things are happening. There's a complex behavior. You get something similar to what you have observed, people have observed in the graphene nanoribbon, where you have an even odd effect. As you go from even number of hexagons to odd number of hexagons. For example, in the graphene nanoribbon, of the armchair heads, you open a gap, you close the gap, you open the gap, you close the gap, and so on. So you get this even odd effect. Over here, you have something very similar. It's a little bit more complex because you have spin over coupling, you also have staggered mass. But if you take the example over here of 3 hexagon wide nanoribbon, now you have odd number of hexagons, there is no end state. And you can see that there is no end state both in theory and in the experiment. So that also matches quite well with the expectation. All right. So here I give you a few more line spectroscopy maps just to give you a complete picture. So over here you still see your end state going to the end state as well. Here there is no end state, so bulk and end look the same, about like 3 hexagon wide. And at 2 hexagon wide, you have it very, very sharp localized. You can even map a 2 hexagon wide nanoribbon, and you see that at these energies where you expect your end state, you have it exactly localized at the end of the nanoribbon. So that is what we think then that we have is we have a nice example of a transition from a 2D topological system to a 1D topological insulator with symmetry protected zero-dimensional end states. This is again the even odd effect I saw you before. You see the phase diagram for different spin orbit coupling, and you see that staggered mass as a function of the width of the nanoribbon, or the hexagon, the number of cells that you have. And you see that you get some behavior that looks a bit like that. So you have a reentrant behavior. So we go from topological to trivial, topological, and so on, depending on these parameters. And we think that we are approximately in this range over here. And for 3 hexagon wide, you see that it's of this topological range for the staggered mass that we have. And then eventually for 6 hexagon wide, it becomes topological. So everything between 3, 4, 5, then for the staggered mass that we have is trivial. Okay, so we can see a width-dependent electronic properties of these nanoribbons. We also see this transition from a 2D to a 1D topological insulator. We can extract out of the lower dimensional limit of the 2D topological insulator, which is about 2 to 2.5 nanometers. And we also now have a new toy, essentially. We have 0D topological states. Can we do something with these 0D topological states? Remember that the system is still backward. Yeah. So we have this honeycomb lattice that is backward. Again, here you see your end state. And what comes out very nicely from the theory is that if you find a way to change your staggered mass, the staggered potential in the due to the backlink, you can go from a topological environment of 1 to 0 for a given spin orbit. So you can go from topological to trivial. Again, we can do the electric field trick of the STM tip. So as we have our STM tip and we go closer to the surface. And then, therefore, we increase our electric field in the system to make it stronger, which translates to a larger staggered mass. So then we wanted to check whether we can go from this to that, so from topological to trivial. This is the experiment. This is the theory for a 2 hexagon wide nanoribbon. And what you see here, this is I don't know, you probably missed a few graphs up there due to contrast, but this is the bulk of the nanoribbon, the experiment part. This is the end with the end state. This is the bulk in theory, and this is the end in theory. And what you see quite nicely reproduced between the two and consistent is that as you increase your field, so you go from low field down to high field, these are all offsetting the curves. So the higher the curve, the larger the field. I don't give you real field values here because the control that we have is the current set point or the set distance of the tip. So it's very difficult to directly give a field, but essentially we simply go closer to the surface. And you see the following happening. You see that the end state disappears. It's gapped out eventually. So you see that you go from having the state to not having the state, and the gap is closing and then reopening. And you see the same thing in the experiment. Here you have your end state, and then it's gapped out at the high field situation. So we have using this electric field, you can think of having a switch, a topological switch, going from a zero-D topological state to a system that does not have this state, so to a trivial system. And you might ask yourself, does this happen? Do you need topology for this? Is it something that is a signature of topology? The answer is yes, because we have tried this in nanoribbons where they exhibit this zero-D states, but somewhere next to it there is some trivial state due to germanium platinum bonds and so on, or junction bonds. So you can see here the topological state in the system. We measure it in a slightly different way. Before we were doing constant height DIDP measurements. Now we do constant current DIDP measurements, and the vision is to be able to resolve this this trivial state of the DIDP better. And we can do this for different current set points, or for low field and for high field. And you see that the only thing that changes, of the big changes dramatically, essentially, is that we get rid of this topological end state. Whereas the trivial state, it gets wider, and it's shifting a bit, probably due to some banding. So this is something that you need topology to induce. And on top of that, you show that you have this complex behavior for this even odd effect that becomes complex because of Stargate mass and spin Hawking coupling in these nanoribbons. So if you look at this is the phase diagram of the 2-hexagon Y nanoribbon, this is here, and this of a 3-hexagon Y nanoribbon, you see that while for a 2-hexagon Y you go from topological to trivial, for a 3-hexagon Y you can go from trivial, that is the initial state, to topological if you increase the Stargate mass, to trivial again. So you have you can, in a way, you can think of inducing topology to a trivial system. So we did it experimentally. So this is what I showed you before. This is the for a 2-hexagon Y, so you can switch your state off, both in theory and experiment. And we did the same thing on a 3-hexagon Y. So this is a low field, there is no end state, and then at high field you see a big emergence there. Same thing with slightly different details for a 3-hexagon for a theoretical part of that 3-hexagon Y. So we have a switch to kill the topological state, but also to induce the topological state in this nanoribbon. And the nice thing is that this is, I missed the slide here, but this is reversible. So we can go back and forth between the states, which could allow in far future for some nice applications if you bypass the other challenges that are out there. So we have, in conclusion, we have a change from a 2D topological to 1D topological insulator. We can see this with dependent electron properties. Again, we have lower dimensional limit of the 2D topological insulator, and we have 0D states that we can also control with an electric field. If I have some more time, I can show some new stuff. Okay. So I would like to show you, this is perturbation that we do with the electric field. This change of the phase there. But you can think of more effects in such a system. So by annealing these nanoribbons several times, we notice that many of them, they end up, this is a nanoribbon, they end up having this bubble-like shape at the end. Sometimes it's attached to the end of the nanoribbon, other times it's detached. And this is emerging when we do a few plus and minus cycles in the system. So there's probably some strain that's happening there. Part of the nanoribbon pops up, then it's retracted from the edges, and then it makes a bubble-like shape. So you can image that bubble, and then you can again resolve the Hohenheim lattice, and you see that it's quite distorted. Especially if you look at the rim of the bubble. So we wanted to see, okay, well, we can see the effect of the electric field. Can we see any effect of this distortion? You expect a lot of strain and inhomogeneous strains in such a system. So these bubbles, they have a size of about 2 nanometers, depending on the size of the ribbon, and a height in the less than a nanometer. So they are small, but they're still quite significant curvature in that system. So we did again DLEV measurements. This is a DLEV measurement of this bubble, and you see this now very, very sharp peaks. And if you do it off the bubble, you see that there are no peaks. So they're very, very sharp peaks that are localized on the bubble. And it's another bubble, a little bit more elongated, and then again, you see all these peaks again. So you have these very sharp peaks at around 0, not symmetric to 0, so there is some doping. And then you have this other more minor or that are coming at higher energies. So we were quite surprised. What is this? We're thinking of different reasons. And what is already known in such a system, like if you take the case of graphene, if you make bubble in graphene, you induce 2 effects. So this is so graphene nanobubbles. Due to this non-uniform deformations that you have, you induce a pseudomagnetic field in the system, which leads to Landau levels, especially when you're dealing with a very high curvature bubble. So this is the theory from this POV here with Katsanas and Yuan. And you see that you have the first, for graphene, the first Landau level, n is 0, which is exactly at the UR point. And then you have n is 1, n is 2, and so on. So these are these green line, very, very sharp peaks. Now, if you go to a bubble with with a smaller height, it also happens for a high height, but then the effect of the Landau level is the strain is lower, so the pseudomagnetic field is lower. So you only see the middle peak remaining in the system, so your N0 Landau level. And the other peaks, before I forgot to mention, they scale due to this linear bounds of graphene with square root of n. The other effect that you have in the system is you get a change in your potential. So if you calculate potential in nanobubble, you see that you have a very high potential in this nanobubble at the edge of the rim of the bubble. So any electron that is within that bubble, then it will feel like it's in a quantum line. So you get confined states on top of that. And you can see these confined states. These are the little bumps that you see over there, for example, in the red bubble, in the red curve. Only when you have bubbles with smaller heights. So the effect of these Landau levels is quite weak. So you have both confined states and pseudo Landau levels. So we also did this for germanene, and we actually can explain this. This is, sorry for the figure over here. I couldn't find the PDF, so I had to start with the PNG. So you see that the first 2 peaks that you see over there, these are Landau levels, and they have the sublinear, what you would expect, dependence. And then the rest of the peaks for this particular bubble follow a linear dependence. And these are these confined states that you would expect for a germanene nanobubble. Now, in contrast to graphene, where you have a Landau level in the middle, for germanene, you get these 2 peaks because you have a band gap. Yeah. So what this helps you to see is that, well, we can see a band gap, the germanene band gap, but also the linear density of states that the germanene has. And what the theory also shows here is that if you change the height of the bubble, or you change the aspect ratio of the bubble, you can go from seeing dominantly your pseudo-Landau levels to your potential or confined states. And we also checked that. So we took a bubble with quite flat, it's quite wide, but also flat. And we compared it to a bubble that is more high, has a higher height. And what you can see here, if you see the blue one, is the bubble with a higher aspect ratio. You see the first N1 over here, N2, N3, and N4, very, very, very strong peaks. You still see the 2 peaks in the middle. And when you go to this other bubble, which is more flat, you only have very strong peaks in the middle. And then the other Landau levels are not visible anymore. And you see you go from a linear dependence of the peaks, which are confined states, to a square root of n, which is the Landau levels. So these are with new results. We are still working on it. We're trying to get statistics, but we think that we have this. We can explore these pseudo-lambda levels also in germanene and not only in graphene. And the nice thing here is that it is quite consistent with the story that we have put forward. So we have a germanene structure with a band gap and then a kind of linear dependence after the band of the density states. Okay, with that, I would like to acknowledge again the people that have worked here. Of course, to thank you for your attention. I think I took a bit more time.
Thank you. Thank you. Questions? Yes.
They had a full presentation. I have one of them is hybridize. So I was wondering, how can you distinguish between each nanoribbon? Because I mean, from the images I saw, like some of them kind of look isolated. There are some of them that are, you have a lot of them. So how do you get control?
Let me show you one image. It's a little bit easier. A lot of nanoribbons. Almost. Okay. Of course, here it's very difficult, right? They are all next to each other. And the other thing that I haven't talked about, that there is something that's happened there, we don't know yet exactly, is that if you have them too close together, then you have things that are happening because the two opposing edge states can't align. In any case, we can still distinguish because there is a gap between the two. There is a sharp transition, then it goes down, and then there's another ribbon on that. So that we can see. But what we have mainly focused, you see over there is a nanoribbon. If you can see it closely, this is a very narrow one, this is a very wide one. And here you have an array of nanoribbons. So these nanoribbons coexist with, I didn't talk about it, with nanowires. So these are it's a nanowire phase, and it's semiconducting, and this within, so there are no states within the energy range of the care. So it's very easy to study these isolated ribbons compared to these ribbons that are very close together. But if you, some samples, it's difficult to find isolated ones, depends on the growth process. Yeah.
Another question
was
more towards the model. Can we explain? But then do you need to start with a critical with the model, and then it works for any bit and any termination of the nanoribbons? Or how do you adjust or guarantee that the model?
So you mean, so if you take a QuMat model?
Yeah, exactly.
Yeah, so if you have something very wide, you have a QuMat topological insulator, right? And then that is your initial starting point. And then you simply start, if I understand correctly, you start removing polygons from your edge, right? And then you make it narrow and narrow. So you need that initial model, right? It's but perhaps you could also start with SSH chain and then build it up. But
I mean, the narrowest QuMat model, if you will,
is it SSH? Yeah.
What we did for calculations is we plotted a variant kit for a cellular boundary condition. So periodic one way over the then you can make it narrow, and you see it's even all behavior. You see the gap opening and closing. And then for the Elvis calculations, the model show that full voltage geometry, where we use parameters from this cellular geometry and calculate Elvis based on.
Thanks.
Maybe also about the terminations of the we also check for the terminations.
In the long duration is always zigzag, which we base on the experiments. And then in the end, you can still choose how to correct the course. There's multiple choice of this. Well, since it's a topological, shouldn't matter too much. But you see the peak shift of it, and then depending on how you terminate it, things shift around a bit, the model will be there. Yeah. We based our final terminations for the work, we based also on the FTMs. Oh, yeah. So, we experimentally it's also very difficult to, we don't have, I mean, you need atomic resolution for every single region that you study, especially at the end. So it's very difficult to
to every time to know what kind of termination we have.
Yes.
Yes. So a little bit more on the zero-dimensional states at the end of these ribbons. The first question is what determines the width of the beat? Because it looks like also in the calculations you see very broad beats. They are
I
very
think
broad. So what's happening here?
I think the calculations are also done for 77 Kelvin. So there is a thermal convolution. So these are the 77 Kelvin data, right? So there is a convolution that we have to the thermal convolution on top of that. Yeah, we haven't deconvoluted to know the exact width. I think the calculations are also
That's
Very complex.
ideal level with the delta peaks. Little bit closer experiment we can call the correlation function. So it's a bit further. So it's
So the theoretical width is a bit artificial.
they are zero.
Yeah, there is the problem.
And then you, I asked already, but that will be the answer. You say something about fractional charges. And
Yes, yes.
And what about spin? So we have different spins on both ends. So what's happening there?
They're both spins.
so that's both. Yeah.
Both spins.
Yeah, they're both spin up and spin downloads. You could argue that together they pass to spin zero. But it really is either spin zero or spin all spin. So there's no fraction.
Yeah. Okay. And but there is fractional charge or variation.
Yeah, there's
First spin is fractional charge.
Push spin.
First spin is fractional.
Yeah.
But this
Like in the SSH.
yeah. So this would yeah.
But if you spin polarized, then you get fraction. If you find a way to get just one type of spin, polarizing, you could get fractional. But it's like SSH, it's not much
In
different.
that case, it's spin over
Yeah,
Yeah. And
all.
this was my last question in terms of general classification. How would you classify this type of topological state?
So
Very similar to
SSH.
that's it.
SSH.
crystalline topological
SSH.
systems.
Yes, this one is a, you could see this as a time of doubled SA models, two codes, the SA.
But this is also nice, right? Because according to the table, you would have the K-Melee for 2 dimensions, but not for 1 dimension. So you lose the K-Melee from the tenfold way in 1G for the quantum spin Hall is not topological. But then you get inversion symmetry and you get topology from a different beam. And that's also something that's nice.
No, I don't speak about X.
No.
I just want to know.
What is nice is that in principle you would lose according to the point from which you started,
It's the
but something else enters in the way and generates topology,
inversion of inversion.
inversion and
I think
divergence.
it will be very the same.
Crystalline inversions.
Yes.
Yeah.
My question, thanks for the presentation. Is there a way of knowing that your edge points, so when you have the wide variance, 5%? And how do you know that these are not localized states? The bringing of your apart from the model, like the model theory shows it, but
I would say, I mean, we also did the electric field on this state as well, on the 1D state on nanoribbon, and we can do the same. We have the same control. So that's one signal that we check. And I don't have the data here to show you, but we did very recently 4 Kelvin measurements, and we see some behavior that is fitting also according to topological states. Yeah.
Yes, please, Diego.
Thanks for the talk. I have a general question. Is it possible to engineer a germanene nanoribbon with no permission or no reciprocal hopping or there?
Don't think so. What you would expect and what you want to have in a structure to
Because
get
you
this.
say that you can create a density of topological states, right?
Yes,
And you can switch between topological and
a
trivial,
trivial.
right?
Oh,
So this would create like a
yeah,
that has a preference current from, for example, from a source to a, I don't know, a drain.
yes.
So this could mean like, for example, like you have a charger and a battery, and then there will be a current
Mhm.
going from the, I don't know, the nanoribbons, because you have this non-emission term, right? So you can create this kind of reference current. That's why
I mean, so if you take the Y nanoribbons, you have this X mode, right? If you put source and drain, we haven't done that. Perhaps an experiment for that would be a pop-up SCM, for example, because germanene, I didn't say that, it's not stable in air, so it's difficult to make device out of it. So you have to do everything vacuum. But you have this X mode, so you have, if you could start with the S current, but I don't know if I understand correctly, because you also mentioned you have this topological trivial. Do you mean to have segments of this topological trivial?
Yes.
Okay, yeah. So what we saw very recently is that you could go from a 3 to 2, and then you also get a state at this cross point. And it's very visible in theory. In the experiment, we also can see it's not as strong as the end point, as the end state. But I don't know how we can use this in a device. And also you have to engineer it that it's in segments, right? That's not, the growth that we do is just, the widths that we get are all grounded, right? And then we just look and we start with the ones that we have. So engineering to have really, I think it's already a challenge to have the same width everywhere, the nanoribbon, but also that you go from 3 to 2 to 3 to, that's even a bigger challenge. But something like this they have done for graphene nanoribbons. And they have started also to follow that. Yeah.
Are there questions online, Mika?
So that's something related to maybe applications. So the way you grow, of course, Germany was coincidental finding
Yes.
the also like this, but for making devices, this is not the way you want to do this. Are there other ways that you would, for instance, be able to make germanene labels, like at least for graphene, they got some chemistry that works and it can be expanded to devices, but are there in the literature other ways of making germanene that you can say, okay, I put it now between the source and the drain, and so I have a gate underneath it, and so on.
So maybe I start with the nanoribbons part. There are only 2 papers for nanoribbons, and both use more or less the same growth. So both they need this metal below. But what I should point out is that, well, if you at least if you look at the regions where they're a little bit more isolated compared to these parallel arrays, the surface around it is circular. And you have a gap that is approximately that a little bit smaller than the bulk germanium gap, the range of 0.4, 0.5 dB. So that could be a part where you could think of putting some contacts and making a device, because then any parasitic current from the bar or anything might be being compared to a system that is, if you take something that's not exactly your of the metal, then it's a bit of a game over. But the thing that we want to do is to find a way to in vacuum, maybe with take a crystal again or something, and then stamping on top of the our crystal with another ribbon, and hope that we pick up some of them. If that works, then you could think of putting contacts and so on. I think the first step is simply in USB to look with the pop-up STM, just take these isolated ones, put contacts, and use a third tip to use 2 tips as contact and third tip as a local gate, and see if you can do like a put principle or concept device.
Maybe a very naive question about the last part on the answer to the nanoribbons.
Yes.
You mentioned that the gap that's in the two peaks are not fully symmetric around zero energy. Is that really expected in these cases?
We think that it's, you mean this, right?
Yes.
So this a little bit closer to zero, this a little bit further away, and it's quite. It also matches to this. This is the same sample that I showed you the data on nanoribbons, and also the peak is zero, the one this day with nanoribbons is also more towards the on the positive side. So we think that this is doping. So you have some doping, and then it shifts into extra states from the front level. And you see the same thing in the peaks. So if you drop the thing and make a bubble, yeah, you see that the peaks are also shifting. But it's not.
Any more questions? Okay, if not, let's thank our speaker again.